Hello, everyone. Good morning, good afternoon, and good evening to whichever part of the world you're in. Warm welcome to each one of you for today's live session on Introduction to Hypothesis Testing. For those unattended about DeFi, we are a data science community which we started with a vision to build data culture and democratize data science learning. And in our endeavor to constantly give back to the community, we regularly conduct boot camps, live workshops, sessions from industry experts, datathons, and other events. Today's session on hypothesis testing is one such initiative, and many thanks to Ms. Julian Joseph for kindly agreeing to do this. Julian, currently a senior full stack engineer and a machine learning engineer at Somnoware Healthcare Systems, has the ability to tell stories through data and helping people make better decisions every day delights the creative engineer in her. For every solution or product that she's been a part of, she strives to build beautiful visualizations and functional designs since she believes people seek experiences, not just products or tools. She has worked on enhancing the efficiency of machine learning algorithms, aligned the expressions into frameworks, pre-processing data to facilitate and calibrating recording according to relevant scopes and signals. Her interest in data science led her to become a Women in Data Science ambassador to inspire data scientists, encourage young girls to choose the field by showing them examples of women using data science in various fields. Once again, thank you very much to Ms. Julian Joseph for joining in with us today. With that, I will let her take over the session.
Hi, everyone. Thank you for joining. It's quite late in India and not wherever you guys are tuning in from. Thank you for joining us. I'm positive you can see my screen. Can somebody give me a confirmation?
Yes, we can see your screen. You can go.
Great. So, welcome to this talk. I'll just begin with a brief introduction about me. I graduated. Thank you for those kind words. I graduated in 2016. I am currently at Somnoware with an ex-Fractalite. One of the reasons, like he mentioned, we in WIDS try to, it's a very simple aim, inspire, educate, and support data scientists, aspiring data scientists, regardless of your gender. Anybody who's interested in this field is try to be educated about this, some concepts at least, or use cases. And if you are in the field, continue to stay in the field because it gets exciting every day. You can find me on Twitter on JustRuin14 and GitHub and Medium, where I occasionally write at GSJ14. So the agenda today looks like this. I'm pretty sure you must have seen this in the registration link. So I'll just go through a bunch of jargons. I'll try to break it down as much as possible. What are the steps of hypothesis testing? We'll be having examples in proportion and in mean. I'll have a brief introduction towards Z and T-tests, and then we'll understand a little in detail about how confidence intervals can also be used along with p-value for hypothesis testing. So as an introduction, I would just like to mention, don't freak out about this entire word about hypothesis testing. It's nothing too serious. In a layman's term, I would call it an assumption. It's a statement that can be further researched upon based on your interest, on whatever you're looking for. And like a lot of you might be collecting your sleep data every day with your Fitband, or and you can have these analysis being done on that, like how well do I sleep during winters, or make some assumptions about what makes you have a good night's sleep. Was it less of social media just before you sleep, or you could have sports analytics being done. There are a bunch of things, metrics that are being tracked by, say, ESPN, or if you've seen how cricketers nowadays, you have these sensors and cameras everywhere. There's a lot of data being collected, and we can use all of the data to actually test against our assumptions. Or you could see it in stock markets, or for example, like if I have an assumption that, okay, currently it's summer and in India, so you might have wheat being, you might get like 10 kilos of wheat for 250 rupees. The reason for that is because you have a lot of harvest of wheat happening here. But that is an assumption that you can actually test against. So it could be tourism, it could be any industry, it could be as naive as I know that gravity is going to work right now, or I assume that gravity is going to work right now, and I can test it. So it can be as complex as you want, or it can be as simple as you want. So, and whenever you do that, you know that you're going to find evidences to actually prove that particular statement. So, like if I were to set at the foundation, you need to know that there'll be two kinds of this. There's one is the status quo. That is a basic assumption. Like, for example, if I were to say somebody, like, you know how a criminal system works, somebody X person is innocent until proven otherwise, right? Until proven guilty. So that's our null hypothesis. I want you to remember this example. We'll go through those examples further as well. But this is what a null hypothesis is always. It is the status quo, and you assume that null hypothesis is true until you find evidence to suggest otherwise. And the alternative hypothesis is something we're very interested in. We want that alternative hypothesis to be true. So we sit and find all of the evidence that we can to actually conclude on that alternative hypothesis. So all our efforts, all the tests that we're going to do, all the T-score, Z-score, F-score that we want to find out is going to be based on, we're hoping that alternate hypothesis comes to be true. Now, let's have some examples so it'll be a little clearer. Also, if you have any questions, feel free to let me know when to pause if I'm going too fast or not. Currently, every news channel, NDTV or news or whatever you guys listen to, if you're an Indian, you know that this person, Sachin Vaze, is there in every news channel. So our null hypothesis is going to be definitely that Sachin Vaze is innocent. And the alternative hypothesis is that he's guilty. So innocent until proven guilty. Always remember that that's going to be your null hypothesis. It could be another example, like how we were talking about whether if you take coffee just before you go to bed, it might take you longer to fall asleep. Now, all of these statements can be tested, can be researched upon. You can find data. Now, what is the logic behind this, and what is the end goal? Like, as a jury, our end goal is going to be just two of this. It can only result in these two things. Our decision can be either to reject the null hypothesis or fail to reject the null hypothesis. When do you fail to reject it? When you don't have enough evidence. There is no evidence to prove that Sachin Vaze is guilty. So he's innocent. There is no way you can go ahead and say that, no, this is you can't, go on gut feeling. This is basically statistics to avoid gut feeling decision making. So you need to have data to actually go by the alternate hypothesis that he is guilty. For example, so always remember, you can never accept. There's nothing called accepting a null hypothesis. You can only conclude upon the alternate hypothesis. So a way I usually try to remember this is H0. You cannot accept it, but HA is something you can conclude upon or accept. So that, because we assume that the null hypothesis is true, basically the reason why we can't accept it is because we assume that it is already true, and then we try to find evidence to disprove that. So we don't know what the reality is. Now, the reality can only be either of these two things. Either the H0 is true or that H0 is false. Now, when do we make the correct decision? When we do reject the null hypothesis, when the null hypothesis is in reality false. And when do we make the right decision in terms of when H0 is true is when you actually fail to reject H0 and H0 is actually true. So these are the only 2 points. Sorry.
Hi, Julian. Just sorry to interrupt. Maybe if you can give some context about the example, right? I think it will be great because a lot of people may not know this example, we have a lot of diverse audience from different countries. So yeah, maybe we can pick a different example or give some context about it.
Sure, we'll go ahead. Yeah. Apologies on that. So it was a trending example in India, my bad on that. So you can go ahead and take your H0 as if you drink, and if and then is not a perfect example, but for example, it could be anybody. Like I can just rename this person, any person who is found to be guilty, or you want that person to be guilty, or you hope that that person is guilty, but it is not true until you prove it until you prove that, right? So ignore these two words, and let's just put anybody that you want there. It could be anybody. I don't want to take names right now, but we'll come to other examples as well. So basically what we're trying to prove here is that your reality can only be either of these two things. Either your H0, whatever your null hypothesis, whatever your status quo is, if that is true, and if you actually fail to reject it because of the lack of evidence to reject that, you have made the right decision. So these are the only two scenarios where the decision is right. I don't want to actually tell the story about this. That's why I'm asking you to just focus on any H0, any status quo. It could be gravity is working, gravity is not working. But currently, if I fail to reject, gravity is working, that H0 as this, you have made the right decision here. So what happens when you make the wrong decision? That is the one point where all the confusion starts, the confusion metrics of data science, the very infamous data science problem starts here. When you make the wrong decision is, even though you have H0 as true, the reality in actuality, the H0 is true, you have rejected that. That is when type 1 error happens. And please don't forget this. We'll go through multiple examples on this, but type 1 error happens when you make that first mistake. When H0 is true, you have rejected it. And type 2 error is when you have H0 as false and you fail to reject it. Ideally, you should have rejected it because H0 is false, but you've not found enough evidence, or you've made some error, and you've had some kind of a mistake that has happened in your collection of your data, or sampling bias. It could be multiple reasons could actually happen. And committing the first error is a little bit more serious than your second error, especially in the case of law. If you actually conclude that somebody is guilty when he's actually innocent, that is it's entirely unacceptable. Now, since we don't really know what is the truth until we see that thing happen, and we might make assumptions before a particular event has happened, we need certain probabilities, and this is where your 8th standard max comes into play, or 10th or 11th, whenever you have studied probability. So probability is basically I'm introducing to you 3 specific jargons which are very helpful for us in the upcoming examples and all throughout, is alpha, beta, and power, where alpha is the probability of committing the type 1 error. How often do you commit this? It can also be called as significance level. Now, sometimes you might actually define this as how much are you tolerant? How much of an error can you tolerate? It might be, say, a food example. Like, for example, I would say the amount of protein in a particular biscuit is claimed to be this, and I'm going to disprove that. So there's a certain amount of tolerance level that you can have, and that is what alpha is. And beta is the probability of committing type 2 error. Very simple. Alpha, beta, first and second. Power is the probability that you would actually reject the null hypothesis given that it is false. So it's 1 minus beta. It's basically just the complement of beta. And since these are all conditional probabilities given that something is happening or not, we want all of these errors to be low, right? Every time you have an error, you want that to be low. But obviously, you can't decrease all of them always. If alpha is decreasing, you would have beta indirectly proportional. So it would increase. So for example, anybody, again, ignore those 2 words as such and was. It could be any XYZ, Mr. XYZ. If I were to just communicate on what that example is, so let me just go to another example. Let's do this. This is another exercise where you have a particular, supposing you are in charge of, you're a civil engineer and you are in charge of signing off whether a particular building is safe. It could be a bridge that is being built, or it could be a new mall that is being built or something. And you have to make this, you have to find out, you have to certify whether a building is safe or not. And there can again be 2 hypotheses in this. So I would actually like this to be an exercise on what you think should be H0 and HA. Again, keep in mind H0 can't be accepted. So you have to frame it in that situation. If there's anybody in the chat, they can actually tell me this. This is an exercise. Like, I just want to understand whether you actually paid attention on what these are the different kinds of things I could mention. But this is a perfect example where H0 is actually coming. Sorry if you saw the solution. Vineet, if you have chat comments coming in from any other place where this is live, do let me know if anyone is commenting on H0.
Yeah, Julian. So probably we need to wait for 5 seconds. There will be a lag of
Sure,
5
sure.
seconds. So yeah, and meanwhile, we can probably pick a question that we have, if you don't mind.
Sure, sure.
So there is, okay, we already got responses. People are saying null hypothesis is building is safe. Okay, we got 3 responses. That's what we got. But coming to the question, right? Someone asked, how is it different? Okay, what is the difference between alpha and power?
Alpha and beta.
Yeah.
So, as I mentioned, there are 2 errors, and there is you don't really know what is the truth, right? So you always have to have a likelihood being created around this, and the probability of committing type 1 error is alpha. The probability of committing type 2 error is beta. How often that happens in a sample of 100 or in a sample of 500, you might actually have that number. You can actually deduct that number as alpha is this. Alpha could be, say, 5%. It is a tolerance level also. Like the significance level, I say it's just 5%. So if I want my answer to be 80 and I say there's a 0.5%, 0.05 is my alpha. So I can have like in terms of 80.5 and 80. There's a plus and minus. There's a difference between these two. There are 2 different errors, and the probability of committing one error is alpha, the probability of committing the other error is beta. Now, for those people who answered H0 is building is safe, I am sorry. That is, if we do that, then what happens? Like, let's just break it down. So if H0 is building is safe, and we end up rejecting that, what will be our, like, we can't accept, right, that building is not safe. So you need to always create your H0 in such a way that you're able to accept HA, right? Building is safe would be your alternate hypothesis, and it is always safe to assume that your building is not safe until you have the evidence for that. So you can't just go ahead and say, haha, that place would be safe, go build. You have to actually check if there's a river going by that place, or if there's a gutter underneath, or if there is a bridge that could be colliding in the future, or of other things that are possible. Like it could be an earthquake prone area. So it's always safe to assume that it is not safe until you have the evidence for that. So you might have lives at stake here. So here, I'm not sure if the image is clear enough. What I've shown here is again that matrix where in reality, if H0 is true, that is, what is H0 here? Building is not safe. And when do you make the right decision? When you, so rejecting building is not safe, when it is not safe is your type 1 error. And when you actually fail to reject it, when it is true, that is the right decision. Now, when you have H0 is false, what is H0? Building is not safe. If it is not safe is false, which means it is safe, then you reject that null hypothesis and you accept the alternate hypothesis. Failing to reject when building is not safe, when it is safe, again, that is also a problem. Like it is actually safe, you have enough evidence for that, you just did not check through properly, that could lead to type 2 error. And the probability of committing type 2 error is again beta, type 1 error is alpha. So keep in mind your selection of your hypothesis also matters. It's just not the error. So I'll just break it down once in a very elaborate way. These are the 6 things that we do. It could be any situation. It could be very complex or it could be very simple. But this is a basic route that we follow. You set up your hypothesis, you check for the conditions, whether it actually is following all of those conditions that you know should be true. Like how I mentioned, H0 and HA. Once you've decided what is your A, not and A, then you have to decide on a significance level, the alpha that I mentioned. Once you've decided that significance level, you go ahead and try to test your hypothesis with that significance level in consideration. What is a test statistic? We'll come to that. Once you've done that test statistic, once you've created that score of that, you have to compare your score of that test statistic. It could be Z, it could be T. Don't worry, we'll get to that, what it is. You have to compare that with a probability value, that is your p-value. Or it can be a different approach, is called the rejection region approach or a p-value approach. There are two approaches on comparison. We'll go through that in detail. And the final thing is basically making a decision about that null hypothesis. Can you reject it, or can you, or do you fail to reject it? And then finally, you have an interpretation and a conclusion for your clients or for yourself. So in case somebody doesn't know what p-value is, we break that down as well. It's a conditional probability, basically. Conditional probability of what? Probability that your test statistic, it can be anything. For now, just assume it is a test statistic. Given that H0 is true. What is H0? Your null hypothesis, the status quo. If that is true, you have to find the probability of the occurrence of that test statistic. You'll have a lot of tables for this. So it's going to be very easy. Finding out p-value is going to be super easy. It's just like how you used to do log, finding out the log values in, I don't know, in chemistry or something. We should have done that. Basically, it's just it's a probability. Don't let that go out of your mind. And when's that probability? That's a number. So all probability is basic maths, 0 to 1, right? Whatever that value is, if that is less than your significance level. So as I mentioned, significance level is decided before you go ahead and do the comparisons, right? So you have a number for that. It could be 5%, it could be 2%, depending upon the criticality of your problem at hand. What is going to happen here is, if it is less, if your p-value is less than alpha, we reject your null hypothesis. It's the yay situation. And you accept your alternate hypothesis. But if your p-value is greater than or equal to the alpha, which is your significance level, you fail to reject it. So that is a situation where you have to either accept that reality or find more evidence, or maybe go ahead and do find out where did you go wrong, or it could be a bunch of other things. Now, basically, it's a comparison, that alpha and that p-value comparison it happens via that test statistics. So normally alpha is 5%, like I kept mentioning. We have 0.05 as that. So what is the test statistic now? We are finally reaching that. I'll explain that through an example. For example, whatever city you are from, let that imagine that town in place of this town, and your mayor is trying to disprove that or prove that you have a national unemployment rate, okay? And he's trying to say that no, that the unemployment rate of my town is not the same as national unemployment level. So your alternate hypothesis is going to be P is not equal to 0.08. Where your national unemployment is, your alternate null hypothesis is that it is the same. So that is what is I've written, that H0 is that unemployment rate of both the town and the nation is the same. So here we have a significance level of, say, 0.05, and that's a usual standard basically. And let's take a sample, take a random sample, say of 200 people, and then the mayor sits and finds out is that person employed or not. But obviously, this is just one small sample. Your city will be or town is going to have a lot more people than 200, but that's a proportion. So we'll be dealing with proportions and means. Here it's a proportion. So your sample statistic is going to be a sample proportion here. So P is going to be 22 divided by 200. Out of that, so what I'm trying to say here is 22 out of them have no jobs. So your sample statistic comes around to be, that proportion is 0.11. Assuming that H0 is true, let's say here, what is H0 again? P is the same. That is, it is the same as a national unemployment rate, right? So here, if you assume that that is true, what are we trying to find out? We're trying to find out whether that result at 0.11 is, how far is it? How far is it from that particular population's proportion, from that assumed population proportion. So p-value is basically how far. Now, if you guys know what a normal distribution looks like, the center is going to be the mean, and how far is your value is your p-value. How many standard deviations away from that true assumed proportion is 0.11. So that is what we're going to find out with Z. This is your Z test, or you can find it out via the Z table. So there's a simple formula for this. This formula that you see here is the population, the sample proportion, P cap minus P0 divided by P0 into 1 minus p0 by n. So there are a lot of ways to prove this as well. I'll be sharing resources on where you can go ahead and find out what are the mathematical proofs for all of these formulas. But using this formula, what I've done here is same as that 0.11, which is your actually that particular sample's proportion, minus 0.08. What was this? The population's proportion, right? That divided by the population proportion, P0 is population proportion, into 1 minus that divided by n. So I'm just basically doing nothing other than following that formula. There is no need to like currently worry about all of the proofs behind this, but you have z scores formulas, you have t score formulas, and all of these z scores can be found out. Once that value is being found out, it comes out to be 1.56. This value is going to be a value that you can find in a table, and the table looks like this. Like I mentioned, old college memories. So here, what I'm trying to find out is 1.56. And if you were to hover over this, I will be getting, if you can see, what is the value that I got here is that particular value when I find in Z table, that is 1.56, I can find the negative and the positive that can be found out. Like it's the same, it's symmetric, right? Normal distribution always symmetric. So if you can find, it's basically distance. So it could be on the left hand side or on the right hand side. So that value comes out to be 0.059. And what is our aim? What was the step? Once you find that particular test statistic from that Z table, your aim is to compare that with the probability value and with the alpha value, right? Where is that? So the alpha value that we had was 0.05. Now, this is somewhat greater than that. So basically, I'm just trying to explain what all test statistics can be. It can be a Z-test or it can be a T-test. Now, T-test is again in terms of, so before I come to explain the T-test, I want to show you one thing. Yeah, this one. So this is a usual flow that we find, that we go through. That is, if your n, the number of samples that you have, if that sample size is less than 30, that is when you go for a T-test. And if it is greater than 30, that is when you go for a Z-test. It's a general practice because T-test actually, if you try to plot that, the values of T, once your value of n is greater than 30, it somewhat aligns perfectly with the Z, right? So this is it's a very easy to go by flowchart, but if you don't keep this, like even after 2 or 4 years, I have always gone back to this. If your data is continuous, if you can find out means, or you're comparing the means of 2 groups, or if you're comparing the variances of 2 groups, based on that decision, you can, if it's variances, you go for an F-test. If it's a mean calculation that you've done and you have multiple groups between which you have to compare the means, you can go ahead and do a T-test. If it's less than 30, greater than 30, a Z-test. And if it's a discrete data, you have a chi-square for that. I'll be going through that in a detail, but I just wanted to show you that, and just keep that in mind, because here, before we jump into this, you need to know when to use what, right? So there's that flowchart was basically for that. Now, a T-test basically is it's trying to find out what is the difference. Like, so there'll be, say, I have a bunch of apples, or I have a bunch of oranges, and I'm measuring the size, the radius, or the diameter of that. It'll be hard to do with all fruits, but you need to understand that there are many different groups, and within a group there'll be differences, definitely, but there could be differences between group A and group B. So what we are trying to find out is, via Dtest, is how significant that difference between those 2 groups are. And if those differences have been just by chance, or has it been because of that particular sample that you've chosen. So again, T-test is also symmetric around about O. And what we see is that in addition to that Z table that you saw right now for the Z-test, in the first column for the T-test will be the degrees of freedom. So depending upon the different degrees of freedom that you've taken, you will have different values for T. And as I mentioned, like as you go, as n keeps increasing, the T distribution looks pretty similar to the Z distribution that you see here. So this is an example of this. Here, the T for 0.05 if I had to find out a degree of freedom 20. So this is going to be mentioned in whatever problems that you're trying to solve. Take any statistics books, ISLR, or any book that you're following, you will be having a degree of freedom. So you have, I think, till 40, because I don't think there's 49. Yeah, only till 40 and you might have degrees of freedom. But I'll just compare, cross verify that. So you take that degrees of freedom 20, and then you find that particular value, and then you can find that what your T at 0.05 is. So if you see the plot here, I have tried to, I think it got cropped, but 0.05, once you have that line, that entire region, that area is what you have as your T value. So if you have certain groups, can you guys see the Excel sheet I'm trying to show? I have an example for this. Is my Excel sheet visible?
No, as of now, we can't see the Excel.
One sec, let me share again. Because I just want to make that T-score via an example. Can you see now? So what you can do this on your own as well, as it takes time to show. You can have a bunch of scores being written for group A and group B, and we can try to apply this formula. Can you see it now?
Yeah, now it's visible. Yeah.
Yeah. So there are like a bunch of steps that you can follow. Let's say there is X is a set of values. It could be like scores of class A and scores of class B. I've basically written them down here. This is your formula that I showed you on that slide there. So in this, what I need to do is find out this D, where this D is actually the sum of the differences between the two groups, right? So what I've done is X and Y has been written here. I've done an X minus Y, and I've done that for all of those 11 values, and I have summed that, sum of D2 to D12. So this is the sum of all of this. This value is going to be written right here, okay? And what is the next value that they need is the sum of the square of the differences. So I've just done 17 square here, 289, and all of these squares have come here, and then I've summed this. Don't square this, just sum this. So this value is actually the sum of all of these values. That also value goes and it's printed here. So this is this D square of sum. This value is going to be the sum of the squares of all of the differences, right? This value is also printed here. N is your sample size here. And this sample size is going to be your sample size minus 1 is your degrees of freedom. So that is how you find out that DF. I forgot to mention that. Now, here you just simply have to apply this value, 73 divided by 11. 73 is your sum, divided by your N is your 11. And you write this value, like do this entire calculation, do this entire thing as mentioned, and you end up with a value called minus 2.74. Now, check out that minus. You can directly go and look for 2.74. But at what point do you have to look for it? At the degree of freedom 10. And then you can find out what that T value is, right? The T value. So the T value here for DF here comes out to be this. Now, again, alpha, generally, if you don't have it, you can go ahead and use 5% and then compare that value. So in this case, since the calculated T value is actually 2.2228 and you have 0.05, right? So this is much greater than 0.05. So when that happens, we can actually come to that conclusion on what is the not an HA on what that value is, whether you can accept it or not. Calculated T value is greater than this. So the P value, which is your 0.05, 0.05, it is less than 0. So I think the question here was whether this is less than this, and we can go ahead and reject that null hypothesis. I just want to show you that it's not rocket science. If you have a formula, if you have a certain set of numbers, and you know you have that data value taken from every group, you can go ahead and apply this. I didn't want you to guys, feel that okay, this is all entirely it's a lot of theory, but I think it is. Let me know if you have any questions so far. Have I confused anybody? Like there is a Z test, there is a T test, and there are different formulas for each one. Can you guys see my screen now?
Yes.
The formula for Z was different. The formula for T was different. You can go ahead and find out different values for all of this from the tables. All of them have different meanings, but eventually you want to find out whether that test statistic, based on the test statistic, the probability that you find for that test statistic, that is this. If I'm confusing you, just go ahead and see this again. That test statistic is the Z score or the T score. Yeah, you have to find that probability. How do you find that probability? From that table. If that value is less than your alpha, you go ahead and reject the null hypothesis. Whatever your null hypothesis was, it could be, I don't know, apples are red, or it could be anything. Like whatever that null hypothesis, you can go ahead and reject that and accept your alternate hypothesis. But keep in mind what we discussed about what has to be your alternate hypothesis and what has to be your null hypothesis. Now, like I mentioned, you could be dealing with means, or you could be dealing with proportions based on what is available here. So in our case of unemployment rate, if you remember that example, this was from the first column that you see, the proportion that you see here. What we are trying to prove is that it is not equal to the national unemployment rate. So in this case, what the type of hypothesis that you end up having is, it could be greater than or it could be less than, right? It could be in either direction, and that's why it's called a two-tailed test. But if the mayor was like very adamant on proving that it is lesser than the national unemployment level, I would go for a left-tailed test. That is, I would say that my alternate hypothesis P is less than P naught. That is where the P that you see here, this is your sample, your town's unemployment rate, and this is the population unemployment rate. But say in some cases it might be the reverse, and that's a right-tailed test. I hope this is clear. And the same thing applies for the mean values. If you are taking the mean of a sample, and if you want to say that it's entirely different from the population one, the sample mean will obviously can be different or cannot be different depending on this. Or you want to say it is greater than, right-tailed, less than, it is left-tailed. So these are different types of two-tailed, right-tailed, and left-tailed. And based on this understanding, we actually end up having graphs and critical regions and all. Currently, we are focusing on the approach of rejecting a null hypothesis based on the p-value. So another question that you can see is, I don't know where all your participants are from, but if we were to find out, are the majority of attendees of the DeFi events, are they from the state of Mumbai, or are they from the state of, say, New York or Pennsylvania? Wherever your state is, you can put that here, okay? Imagine that is there. So what is our response variable here? It is state, and it's a qualitative variable. So your parameter of interest would be that proportion of people from your attendees. If you have, say, 200 people attending right now, let's say 5 of them are from Mumbai, right? But what is our hypothesis going to be? We are actually looking for that majority. Is the majority of attendees of these events from this particular state that we're looking for. So again, your P naught here is going to be at 50%, right? Majority is decided. If it's more than 50%, then that's majority, right? So 50%, P0 is going to be 0.5, and majority also implies it's greater than 50%. What is this test going to be? It's going to be greater than, so it's a right-tailed test. Your alternate hypothesis is that P, that proportion value that you find out, is greater than 0.5. So I just want that clarity to be there. And you can't just go ahead and say, okay, this is a left-tailed test. You have to have that understanding clear on, this is clearly my alternate hypothesis. I want this to be greater than 50. Only then I can say that the majority of my participants are from a particular state. It's a qualitative variable, right? Another example would be, say, for now, all of you, when you registered, DeFi's website was having a green header and a white background, right? Now, say for tomorrow, one of you guys say, Vineet decides, no, I'm going to change it from green to violet, and the background from white to yellow. Whatever, it could be just an A/B testing, right? Currently, your mean visit time of a person going through the courses available, the events available, the different dates, the different times, different speakers, and all of that amounts up to be 20 minutes. Okay, so we are going to find out whether changing, when Vineet says, I'm going to change it from white to yellow, and say, and he's claiming that that's going to increase the number of visits to our website, we can actually test that hypothesis, right? So the hypothesis is going to be that your mean visit time after the change of that white background to yellow background, even then it does not change. And because white, again, alternate hypothesis is that he is trying to prove the fact that mean visit time is going to be more than 20 minutes after that change. So that is why we've kept that. So since he wants to accept that particular thing, we've kept it at HA. Please remember that again. What we want to accept is what we want to keep here, right? So your null hypothesis is status quo, that's not going to change. What's going to make a difference? Again, significance level of, you have a tolerance level of 5%. You take a sample of 100 people who are visiting this website. There are two sample versions. One is on a testing environment where it's having a yellow background, and one is having a white background. So we keep testing what are the average visit times. And supposing it turns out to be having a mean of 25 minutes, then what is that particular thing that you've found out is that mean, for that particular mean, we are now going to find a probability, because p-value is not that 25 minutes. Don't confuse that. P-value is going to be the probability that you have mean value greater than 25, greater than 20, or equal to 25 here. It should be equal to 25, provided that H0 is true, right? We find that p-value using whatever methods we need to find out. And if that p-value is less than alpha, that is less than 0.05, you reject the null hypothesis. If it's greater than this, you can't reject. Say, for example, the p-value comes out to be 0.03, right? In this case, this is less than 0.05. So alpha is 0.05, 0.03 is less than that. So we reject the null hypothesis, saying that it is going to remain the same. It will increase. So Vineet is going to be like, yay. But if it's the other way around, say an example of, say, 2, you won't have it greater than 1. Let's say it has 0.6, right? So that value is going to be greater than alpha. And in that case, we reject the null hypothesis. I hope this much is clear. Let me know if you have any questions. Now, the next step after having calculated that, if you remember the order, and to show you that again, we know how to create hypothesis. Now we know what a significance level is. We know what are the different kind of test statistics there are. We know how to find the probability value. I have not discussed the rejection approach right now. I'll go to that. But the next is basically creating a decision. So how do you make that decision? And use, again, we were making a decision using the p-value. We can also make a decision using the rejection region. So here we go. Once we have that null and this is being done, and we know what is the, we also take care of whether we have made how much of the alpha is there, whether we can actually incorporate that much of an error or not. So I hope you all remember what alpha was. So either you have to determine that particular value based on that alpha value, right? We have that p-value approach, or the p-value approach is basically finding out that p-value via that conditional probability that you find out if that is greater than alpha or not. The other approach is this. Once you have a particular region, that region is basically, once you know, say alpha is at this point, you have that alpha at 0.05. Here it's minus 0.05. Whatever region that you see beyond, I mean, less than that, that area is called the critical region. And if your value lies in that region, H0 is going to be rejected, right? You have to reject. So this is a case of a left-tailed test. Here I'm trying to I'm expecting that my test statistic is going to be less than or equal to that critical value. So this is basically the second approach that I was talking about, where that region entirely helps you decide. If it comes anywhere beyond, in the negative annotation, beyond CA, that is your critical value. Critical value is going to be that particular value on that normal distribution pertaining to alpha. And you can have that on the right-hand side as well when it's a right-tail test. If it's greater than that C value, here it's C1 minus alpha. So because this side of the complement of alpha is going to be 1 minus alpha. So this is called the 1 minus alpha is the region where it's called the confidence interval level. If it's falling in this region, 1 minus alpha region, you can go ahead and if the null hypothesis lies in this particular value, we'll come to those examples when we discuss confidence interval. But for now, focus on that orange area that you see. This value, wherever, if your test statistic is lying anywhere here in this region, you can go ahead and reject that. Okay, reject the null hypothesis. So these are the two ways that you can decide. Either you determine based on the p-value approach, or you determine based on the rejection region. Where if our test statistic, like your value could be, say, these values that you saw, the value that you saw here as 1.725 or any of these values that you get from your test statistic, if that lies within that orange region, you can go ahead and reject that. Okay, and the same applies for, there's also a two-tailed test where you could have both kinds of values, minus and positive. And in this case, we make use of alpha by 2. So it could be if you can reject your null hypothesis if that particular value of that test statistic is greater than or is greater than this, or it's equal to that particular value, that C alpha by 2. So all of this has been with the assumption that you all know how normal distributions are created for different samples. It could be any sample with even thousands of your sample size being even 1,000 from, it could be different kinds of normal distributions could be created. And once you, provided that your the samples that you're taking and the test that you're making is having a normal distribution, all of these things stand true, the left tail and the right tail, right? We've gone through this, but there's also F statistic and there's also Chi-square. So Chi-square actually comes into place where you know that your value, the data that you have is actually discrete, and you have an observed value and an expected value. You're going to compare those two, like how I mentioned, comparing differences between these values for test case for the T-test. And in T-test, mainly it's the mean. In F-test, you can find it between variances. There are different formulas for each of this. And here, Chi-square, like in what I showed you earlier was the test. So in this, the formula for T is different. It is the mean, is the difference between the means that I've done. What I was doing in the Excel sheet that I'd shown you, we were comparing the differences between two different groups, right? And in those two different groups, what we took was we were finding that particular T-score. And if we deep dive into each of these things, all of them have different formulas as well. I can take a different session on explaining how those formulas came into place. It's a very beautiful way to understand that. I will leave this right now in the interest of time, because we want to find out, you remember this area that I'd shown you, 1 minus alpha area. This area is very interesting for us because that confidence interval is going to be lying there. Let's move to that. Confidence interval is, so when I mentioned we can find out a particular value for a particular population, you might have, you can go ahead and find a particular mean if you know all of the samples, right? So, but in a huge population, that's not really the case. You don't really know what that entire population's mean value will be. You can only take a sample and then find its mean, right? So for an entire population, you will have that particular variable that you want to estimate. And for that estimation that you want to do, you'll have a range. You can't actually go ahead and say, hey, this is going to be the exact value or the exact mean. So for that range, confidence interval is that sample mean plus or minus the margin of error. So mean for that, whatever variable, it could be the height of, say, women in India or in US, or it could be whatever mean that you're trying to find out for that population. It is estimated by using this confidence interval. It can lie between a certain range. And confidence level is a different thing, where you remember alpha was a significance level, right? So 1 minus alpha is your confidence level. If you say your alpha is 0.05, the corresponding confidence level is going to be 95%. So you can claim your research conclusions with 95% confidence level. That's one. So whatever method that you followed, it will have the same results on a 95% basis, right? So we'll have examples for each of this. So please note there's a difference between confidence interval and confidence level. I hope that's clear. Just ping me please ping on the chat if that's not clear. I'll repeat that with different examples. So here what we have is, let's say the sample mean is 80, okay? Like I mentioned, you can't go ahead and do the population mean. You've taken the sample, you've taken the mean of that turned out to be 80. And when that happened, we also have we know that the margin of error is 3.92. So when I want to say that my confidence level is 95%, I'm going to find out the confidence interval. Remember, the confidence interval is that sample mean plus or minus the margin of error. So margin of error is 3.92 plus or minus the margin of error is going to give me 83 and 76. So it is going to lie. This is your interval between which you can have the population mean variable, but it is with a So when I say this is, when I say 95% in the bracket, I mean that my confidence level is 95%. So you're going to have that much of confidence saying that, because no matter which sample you take, supposing on Monday you take sample of the first 100, on Tuesday you take the sample of the next 100, you can have n number of methods being n number of means being calculated with that. You will always have, you'll have a confidence of 95% that you're going to end up with the same. Here I think it was a motivation score of a person, or it could be happiness index of nations or countries, or whatever is your objective. It will lie between this range, and you can say these two numbers as the upper limit and the lower limit with a confidence of 95%. So this is an example. Basically, if there was a baseball coach who's curious to know what is the speed of a ball that is thrown, the fast ball thrown that is thrown with a certain speed. So the speed is measured in kilometers per hour, and let's say take a random sample of 100 pitches, and this is considered again with a confidence interval of 95%. Remember, alpha is always decided earlier on, so you know that the tolerance level is there, so you know that your confidence interval. So in this case, when you have with 95% confidence, you end up having an interval of 110 and 120. Okay, supposing you end up with this upper limit and lower limit, what we're trying to find, what we end up like, in order to interpret this, we would say that the true mean of that pitch, the pitch speed that they're finding, he's actually trying to find out that speed, that mean speed. That is, we are going to be 95% confident about this, that it will lie between 110 and 120. So it is actually, so that range that is actually possible. It could be 110, it could be 111, it could be whatever, 115. A range of possible values are there. So if I say my 95% is my confidence level, and I want to increase that to say 99%, maybe it's a very critical match for this particular coach, and if he has to increase it to 95%, 99% from 95%, he will have a larger range. Why? Because that error will also increase. If you want to increase your confidence level as well, your interval, you will end up having a larger margin of error. So that'll have a wider range. It'll not be 110. It'll be like, say, maybe 108 to 122. The range will also increase. That's how you interpret a particular interval. For the level, if I were to take an example, here, say it's voting time, and you have 500 voters who say they support a particular candidate or they don't. Now, for example, in this case, if we have the result of that sample, and we have 90% confidence rate, that the proportion that sample is, if that sample is pro for candidate A, that is going to be the true case for the entire, when the entire election is over, it is the true proportion of all of the voters who support that candidate. We have not taken the entire sample, we've just taken 500 voters. There'll be definitely more than 500 voters, right? So if the pollster keeps, and if we say that we have 90% confidence for this particular example, what we are actually trying to say is that if the pollster is going to repeat his process again and again, and so let's say he takes 20 intervals, or if 20 times he does that, 18 of those 20 intervals will contain that true proportion value. So level is again the now how often. So I'll just repeat this part. Level refers to the long-term success rate of that method. You do one thing, and if you keep doing that again and again, it's how often you'll have the same thing and that true value. If in this case it was the true proportion value of those voters. So that stated confidence level is that 90% of the time you're going to have the same value, right? So 18 of 20 is actually 90%. In terms of confidence interval, it is that range of values between what range we can expect that mean to exist, in that mean pitch speed that we discussed. So these are the two differences. Don't confuse there. And we're now having, what we're going to try and do is we're going to compare our p-value to our confidence interval, right? So if you remember, we used p-value with our alpha significance level, or the thing that we're going to use for our confidence level. So it's all the same. Like if you, like I've not introduced anything new here. Alpha, 1 minus alpha is confidence level, right? And whenever we knew a particular test, you can actually go ahead and find out just p-values and go ahead and conclude, or you can find out the confidence interval and confidence levels and then conclude that. But supposing your test ends up, and you want to just verify your test, and you find out everything. You find out p-values and you find out the confidence level. Both of these statistics are going to give you the same answers. They're both going to agree on this, on the conclusions. Why? Because what they're trying to do is they are trying to find out the distance from the mean, and that distance is going to be the same. So we'll just go through one example here. So if your p-value is, so whatever your p-value, so based on your p-value and your alpha, what we were trying to do is we were trying to find out whether we want to reject a particular thing or fail to reject. That is, people end up using the word called statistically significant. What I mean by statistically significant is that whether I have enough data to actually abide by that, or if whether I have enough data to actually conclude that this particular thing is correct or wrong. So you can use either p-values or you can use confidence intervals. Both of them are going to agree, because whatever, so like if you remember seeing this chart, understand this in a visual way. You are actually trying to measure the distance from the mean, and it could be how far is it or how close is it, right? It's going to be the same distance. So once your distance is the same, your conclusions are also going to be the same. If your p-value is less than, so what were you trying to do? If your p-value is less than the significance level, the hypothesis testing is statistically significant, right? You're rejecting your null hypothesis. If the confidence interval does not contain that particular hypothesis value, the results are significant. So again, what is a confidence interval? This value. Sorry, I have to keep going back. 1 minus alpha, confidence level, remember? So if this does not consist of that, you can go ahead and reject, right? And your results are statistically significant. If p-value is less than alpha, the confidence interval will not contain that hypothesis value. What are you looking for? So in terms of a two-tailed test, what I was trying to show you there was we can actually find out, again, it's the same thing, that if the hypothesis value is falling within that interval, we fail to reject, right? And if it is interval as in that value as in the orange area, if it is within that orange area, we fail to reject, right? And if it is within the, if it's outside that interval area, it is, we reject the null hypothesis. So CI, that is confidence interval, for let's say we have 95% confidence interval for this particular example. In this, there's a random sample of 1,500 adults in West Bengal, or you can again take it. I'm taking Indian examples here, but it could be any election that's happening in that's going to happen in your state. Maybe, okay, let's take Biden's example globally. If it was US adults, 1,500 of them have been taken as a random sample, and they have been asked whether they approve or disapprove of the current president. Let's take Trump's example. If this test was happening in the months of October, so what would be the president's approval rating? And if, say, out of those 1,500 people who have been surveyed, 660 people respond with an approve, they approve of Trump, and the rest 400 or plus folks have actually disapproved of Trump. So if we have 95% confidence level for this, and we end up having, like, I've done a test for this and I've seen that the values actually be the interval that I figure out for this particular range with a 95% confidence interval, we can go ahead and just do those calculations that we have for any of those tests, and we get this value. If I do a t-test here, I get a value of 0.415. This is my upper limit, and my lower limit is going to be 0.465. So if I have a hypothesis and I want to prove, I want to test whether that approval rating is going to be different than, it's going to be less than or greater than, it could be either of this, than 40%, then my hypothesis is going to be tested, set up like this. H0, where P is 40%, and I'm saying it could be different, so it is not equal to 40%. We are going to decide on a level of, say, 5% as significance level. And when we try to do this value, I use Dtest to find the confidence interval. I can go ahead and use Dtest to actually find out, prove this particular hypothesis, test this particular hypothesis, that the proportion is going to be different than 40%, right? So what do I have to do? It's the same formula. Your sample that you figured out was 660 of them have approved. And from that, you find out what your entire P0 that you're finding out is 40%, so 0.4. And you do the square root of 0.4 into 1 minus 0.004 divided by, again, n is your sample. You took a sample of 1,500 voters. So you end up with a value of 3.16. So this is your step 3. Steps are always the same. Whenever you do a hypothesis testing, set up your hypothesis, the two hypotheses, decide on a significance level. Step 3, calculate that value. Step 4, calculate your p-value based on that value. So you found 3.16, and you will take that z table that I showed you earlier. You'll find out what that z value is, and then so here, since it's a two-tailed test, remember I mentioned if it's greater than, I just need to do 1, but it's a two-tailed test. So that's I've done 2 into this, and 0. This is the value that turns out from the table. So when I do this, this value turns out to be here. What was my significance level? 0.05, and here it is 0.00156. Far less, right? So when that decision, so based on that value, our next step is to make a decision. And that is that we can reject the null hypothesis, that it is, if you say, if your null hypothesis, what was your null hypothesis, that it is equal to 40%. And when we reject that, we have to accept the alternate hypothesis that it is greater than or less than. It is different from 40%. So how did you use that confidence interval? If you look at 95% confidence interval for that particular test, it was 0.415, 0.465. 40% is not within that, right? We can easily go ahead and look at that directly and say that this is how we can conclude that this null hypothesis can be rejected. So this is how, like, if you can see 0.40 is not a part of this, right? It's after that. So the confidence interval itself is enough for you to connect that value. And I've proved that via the normal process that we were following. The last thing that I would like to leave you with is that there is this empirical rule that keeps coming up. You might see it as 68, 95, 99.7 rule as well. What that also means is it's very simple, actually. Like I've been mentioning, your center of the graph of normal distribution is your mean. And what you see most often happening is, so 50% of the data is here, 50% of the data is here, right? So whatever is below the mean and whatever is above the mean, that is going to constitute of just half, like exactly half. Now, if you were to figure out what happens, so if you see this distance between that is 0 and the part where this purple line ends, that is this 34% where this is ending, this is one standard deviation. The standard deviation is that one distance between your 0, this line and this line. This is one standard deviation away. 2 standard deviations away is this. 3 standard deviation away is this. So every sample, you can find the mean, you can find the standard deviation, you can find the variance, right? There is a formula for that, and you can go ahead and find it out for anything. But whenever you do that, what we see is that if it's a normal distribution, if your data actually follows a normal distribution, almost like exactly 34% of your data is going to be that one standard deviation of distance data, and 68% is going to occur within that 1. So when I say within 1, I mean the plus and the minus. This entire one thing is their one standard deviation, right? 2 standard deviations away is the 95% of your data is going to be approximately, it's like, it could be like 94.99, or there'll be some decimal places, but approximately 95% of your data is going to be within this two standard deviations away from the mean. Similarly for 99.7. So an example for this, like on how do you use this on an example was like through this example, I'm just portraying this. If the diameter of a basketball is normally distributed with a mean of 9 inches and a standard deviation, you have calculated what your standard deviation is for that particular thing, is 0.5. Now, if you see 9 and 0.5, so what I mentioned was one standard deviation away is going to be 9.5. 2 standard deviations, 10. 3 standard deviations, 10.5, right? So your question is, what is the probability that a randomly chosen basketball is going to be having a diameter between 9.5 and 10.5? If you have this as your question, you can just directly go ahead, your standard deviation already. 9.5 and 10.5 is here. So you can just go ahead and add 13.5 and 2.35, right? So knowing these things, because it is a normal distribution, this is what is going to definitely happen. Like statistics will have proves that for you. So you can directly just go ahead and apply this rule. It's an empirical rule, doesn't fails for, if it is normal distribution, it's definitely going to work. And I've crossed by 5 minutes, sorry. Please go ahead and let me know if you have any questions. And I couldn't cover a lot of the math of this, but it's very easily available. I can share the resources. I've used Khan Academy and University of Pennsylvania. The course name, I can mention the course name on the chat actually. Where is the chat? Can you guys see the chat?
Hi, Julian. I think you can share the resources with us, and we'll put it up on YouTube. So
Sure,
basically,
sure.
it's
Doing that.
streaming on YouTube, and we have a few questions
Go
out
ahead, go
there.
ahead.
I'll probably read it out.
Mm.
Yeah, so we have a question. What is the difference between descriptive statistics and hypothesis testing? Why hypothesis testing?
Could you repeat?
What is the difference between descriptive statistics and hypothesis testing? Why hypothesis testing is the robust method when compared to descriptive statistics? This is one. And yeah.
So hypothesis testing is when you have these assumptions being made, right? And when you do descriptive statistics, I think for every data set that you have, I mean, it depends on your objective, right? Like you can have, if you have enough information on that particular data set that you have, understanding statistics via mean, median, mode is to an extent you can do this. And what you can go ahead and do with that is you know what you can do with the mode, what you can do with medians and all of those statistics, right? But hypothesis testing is when you have those different situations, right? You know there is a prove or find evidence against. I think descriptive statistics only. Okay, so using me a mode of a particular value data set, I can't go ahead and like there is no score against which I can like there is no margin of error that I can verify this against or compare this against. They're entirely different. Like they're used for different things. Like mean is for average. You know that this is the average of particular thing. But when you are referring to populations, when you're referring to places where you can't really go ahead and a country might have millions and millions of people, right? And when you try to find out the mode or the mean, say mean height of a person, right? Let's say in India, there is a statistic that says average height of a woman is 5 feet, and I am say 5'2", okay, 5'2" or 5'3". So I'm as a person, as a researcher, I'm going to collect data from every single state in India, and I'm going to disprove that. And my null hypothesis will be that average height of a female in India is this much, is 5 feet. My alternate hypothesis is that it is not going to be this. So mean is just going to give you mean, but hypothesis testing is going to allow you to do that A/B testing, right? The website testing that we showed. There are different versions of this, right? You can go ahead and test, find data for disprove for rejecting that null hypothesis that they have only 5 feet. It could be more than that, it could be less than that. Maybe the next generation is going to be like all of them going to be 6 feet tall. It could be anything, right? Based on the data that you have. So there's a limit to what you can do with distributed statistics, and there's a limit to what you can do with hypothesis testing as well. But depending upon your scenario, it keeps changing.
Yeah, probably we'll move to the next question. How to decide value of alpha? I have seen comparison with 0.5, 0.1, etc. Different values of alpha completely change the result of hypothesis testing.
Correct. So that's again the amount of tolerance you have for a particular value. So like I mentioned, so supposing you are testing the effectiveness of COVID vaccine, or something even more serious, like something that has a fatality rate of 90% or something. God forbid something like that happens. But if you were in charge of testing the efficiency of a particular medicine, or testing the safety factor of a medicine that you're going to release in the market, you need to be really sure and have very less tolerance level, right? Based on that criticality of that particular objective in mind, you will change your alpha. So most often you see it as 5%, but there are cases when even 5% is a grave mistake. You can't risk with people's lives, or you can't risk with the health of a child. Maybe you're releasing a medicine only for pediatrics. You can't really risk that, or maybe it's just one particular biscuit that you're releasing into the market, and you say that this has medicinal values. So depending on your how serious that particular error is, if you commit that error, the probability of that will change, right?
Yeah, true. And Yeah, so there is another question. I think this was very specific to one of the slides. Shouldn't the null hypothesis be less than or equals to 20 rather than equal to 20? I think this was somewhere in between. So maybe
I can
if
share
you,
the slides. I
yeah,
might have made a mistake because I was trying to include as many examples as possible,
okay.
just to make it clear instead of just making it theory. If you could just remind me of which one it is, I'll just try to find out, and if I find this, I'll just share that.
Yeah, sure, sure.
The values.
Again, like, it's just a question. He's not
Sure,
sure whether it is right or not, but even maybe
sure,
you
sure.
can validate that and update the slide and send it back to us.
Definitely.
Yeah. And
Searching.
there is another question. What is meant by margin of error? Is it significance level or something else? If so, then what is the difference between significance level and margin of error?
Significance level is your probability, right? Probability of committing that value, that error. So margin of error, it will so you know that your confidence level is based on that, your confidence interval is based on your margin of error. That is what we had gone through during the slides, right? But margin of error is just that. It's like how many percentage points you will actually, your results will actually vary from that real population value. What are we trying to do all throughout this time is we have a huge population. We want to find out some particular characteristic feature of that population. We go ahead and take a sample, and that sample will have a particular statistic value. It could be mean, it could be mode, it could be median. And I want to say compare that mean sample value with my population sample value. So how many percentage points it will vary is my margin of error. It is going to be 5% or 4% or how many of a percent is that percentage is your margin of error. Like in one of the exams that we're taking was 3.92 was the percent margin of error. So 83 and 76. It's just that difference between that mean and that population, sample mean and the population mean, or it could be median or proportion or whatever is your statistic that you're trying to find out.
Yeah. And in accordance to the research questions, will we do hypothesis testing? This is a question. Yeah.
Sorry, what?
So this is a question. Even I'm not sure, like, if it is complete or not, but in
Yeah.
accordance to research questions, will we do hypothesis testing or will we arrive at hypothesis testing? Maybe this could be the question. Yeah.
Yeah, I mean, definitely. So all you could go ahead. So like I mentioned in the beginning, you can use hypothesis testing for anything. It could be randomly, like if I assume my flight of stairs is going to be there when I take that, so I can go keep walking and keep testing whether it's there or not. So researchers obviously can use it. So if I can use it for something as trivial as that, as testing gravity, I can test it for really complicated research as well. Whether it could be how viral a YouTube video is, I can test it for that, or I can test it for n number of things, like whether a particular weather is going to be suited for a particular sport or not, or the rate of gold is going to change or not. That comes to around prediction, but I can have assumptions around that and then predict that. So regardless of what your research is in, if you have these hypotheses, these assumptions, and you want to test that particular assumption, you can go ahead and use this. Yeah.
Okay. And we have one more question. How shall we frame the hypothesis when we want to prove the null hypothesis? Example, in the unemployment example, let's say I want to prove that unemployment is 10%.
So if you remember the building is safe and building is not safe example, that is the perfect example for you to understand how to create that hypothesis. Now, when you say prove the hypothesis, again, always remember you're trying to collect data to either reject or fail to reject that particular null hypothesis, and so that you can go ahead and conclude on the alternate hypothesis. Now, in terms of the example that you've stated, if you want to prove that the unemployment rate of your town is 10%, that is going to be your alternate hypothesis. That's something you want to conclude on. And your null hypothesis, that is not going to be that. So depending on what you want to accept, you go ahead and decide what your HA is going to be. And if you don't want to accept that, so until unless you have evidence, you can't go and say that that is true or false. So you have null hypothesis always as status quo. I hope that's clear. And what you're going to look for is whether your building is safe, whether your unemployment rate is 10% or not, right? By that alternate hypothesis. Should I go through that example again, or do you want to see the slides again?
I think, I'm not sure. I think maybe it might have addressed. If not, I think we'll probably,
Sure,
they can probably get in touch with you later.
Sure.
Okay. And I think that's pretty much, we are done with the questions. We have a few more, but I think they were addressed on the chat. Okay. And thanks a lot, Julian, for the session. I think it was insightful, and we had a lot of queries on the way. And before we wind up, any quick thoughts and any learnings that you have had as a machine learning engineer or a full stack engineer? I mean, basically, you would want to share that knowledge or experiences with the community. Yeah, that will be great, I believe. Yeah.
So I've started as a my professional experience was started with front-end engineering, and this is completely out of interest that I picked up back-end engineering, Python and data science. So if you are a newbie to this, regardless of who you are, like if I can do this, definitely you can do this, and go ahead and spend your weekends learning statistics. Like though you people are calling it AI in the investor meeting board meetings and all of that, eventually boils down to, if you can actually understand the statistics and the math behind all of this, you need to spend your weekends on essence of algebra is there on 3 blue 1 brown. There's this beautiful channel for math. Brush up on your math skills, brush up on statistics. ISLR is one of my most highly recommended book that you should definitely go through. And pick up on things that are basic first. Like, don't start with reinforcement learning and lose your way there. I love the fact that you have these communities with, DeFi is doing a great job in bringing you live sessions. So make use of all of these communities. There are multiple ways to learn this, and keep learning. Like I would say, regardless, it's like I started my journey in 2018 and I'm still learning. I keep going back to the basics as well. There is no shortcut. You need to make sure, if you don't know how to interpret your final result to yourself or to your clients, you need to go back to the basics. And that's one of the reasons why I chose such a very basic topic. And this type 1 error and type 2 error is going to help you decide a lot of things in your very complex models as well. So make sure you brush up on the basics. I will just end with that.
Thanks a lot for the wonderful piece of advice, Julian, and thanks once again for joining in, and also thanks for some of the moderators out there, like Raviraj, was chipped in to answer a few questions on the chat. Thanks a ton, and take care. Yeah, bye.
Thank you for the opportunity.
Thanks.